Welcome to this video about the impact of application architectures on data operation. After watching this video, you will be able to explain the role of application architectures in data operations, focusing on their impact on data ingestion, integration, storage, and management, and evaluate the influence of microservices and cloud-native architectures on data processing, analytics, security, and governance. Application architectures are essential in defining the design, efficiency, and scalability of data operations within an organization. As distributed systems, cloud-native development, and data-intensive applications grow, their connection to data operations has become increasingly complex. Understanding how different architectures impact data operations is vital to optimize performance, minimize cost, and ensure seamless workflows. This clarity enables organizations to navigate complexities effectively and improve operational outcomes. Let's understand the role of application architecture in detail. Application architectures are how applications are designed, deployed, and interact with systems. These can be classified into three types. Monolithic architectures are single-tiered and tightly integrated systems. Service-oriented architectures, or SOA, are modular systems with components communicating via defined interfaces, and microservices and cloud-native architectures are decentralized, independently deployable services optimized for cloud technologies. These architectures uniquely impact data operations, shaping how data is ingested, processed, stored, and accessed. Let's evaluate the influence of microservices and cloud-native architectures on data ingestion and integration, storage and management, data processing, analytics, data security, and governance, and apply this knowledge to optimize organizational data workflows. Monolithic architectures rely on centralized data ingestion pipelines, where tightly coupled components simplify data integration but reduce flexibility. This approach offers advantages such as easier management of a single data flow and predictable data access patterns. However, it presents challenges like scaling the entire application to handle increased ingestion and difficulties integrating with external systems or real-time data sources. Microservices and cloud-native architectures tend to favor decentralized data ingestion. Here, every independent service can maintain its pipeline. While this will allow parallel ingestion from diverse sources and improve scalability for real-time processing, it introduces complexities like ensuring data consistency across services and managing schema changes or API versioning. The best practices to address the above challenges include using event-driven architectures like Kafka or RabbitMQ for the ingestion from real-time sources and using the data, APIs, and schema registries when standardizing the integration across services. In monolithic setups, a single relational database is the central repository for all application data. This makes data management with a unified schema simple and will reduce the need for frequent replication or synchronization of data. However, as application usage grows, the database becomes a scalability bottleneck and introduces risks of outages due to single points of failure. In contrast, microservices and cloud-native architectures would use polyglot persistence, where each service would have a dedicated data store tailored to its specific needs. This would boost performance using NoSQL for unstructured data or graph databases for relationships and scale and tolerate faults through decentralized data management. However, it also brings challenges such as increased operational overhead in managing multiple storage solutions, which increases complexity in enforcing governance and compliance. Best practices include adopting a data mesh strategy to decentralize data ownership while maintaining governance and implementing centralized monitoring tools for distributed databases. Data processing in monolithic systems is often batch-oriented and relies on extract transform load, or ETL pipelines. This makes for simple, predictable workflows and has proven suitable for traditional reporting and business intelligence BI. However, flexibility is lacking to meet real-time or near real-time analytics demands, and processing large-scale data tends to suffer from high latency. Microservices and cloud-native architectures, in contrast, both support batch and stream processing by allowing data to be processed closer to its source. This means real-time insights, faster decision-making, and distributed data processing frameworks like Apache Spark or Flink. However, it is accompanied by the following difficulties: orchestration of workflows across distributed services, ensuring near real-time data synchronization and consistency, and pipelines. The best practices in such scenarios include leveraging event streaming platforms like Kafka Streams for real-time analytics and containerized processing environments for better scalability. Centralized architectures simplify security and governance by consolidating data in a single location. This makes it easier to implement access controls, compliance checks, and unified audit trails for regulatory reporting. However, because of their single-point vulnerabilities, they are also more susceptible to massive breaches. Microservices and cloud-native architectures are decentralized, so security controls must be implemented across multiple services and databases. This can lead to fine-grained access controls and increased fault tolerance, but increases the likelihood of configuration errors that result in data leaks and complicate compliance tracking across distributed environments. Best practices to mitigate these risks include using zero-trust security models to enforce strict access controls and employing tools like AWS IAM, Azure AD, or Google Cloud Identity for managing distributed identities. In this video, you learned that application architectures significantly influence data operations, shaping how data is ingested, stored, processed, and secured. Monolithic architectures simplify centralized data management, but struggle with scalability and real-time needs. Microservices and cloud-native architectures enable decentralized, scalable, and real-time data operations, but introduce integration, consistency, and governance complexity. Data ingestion in modern architectures benefits from event-driven systems, while polyglot persistence enhances storage efficiency. Finally, you also learned that real-time analytics thrive in distributed setups, leveraging stream processing frameworks. Security in monolithic systems is centralized but prone to significant breaches, whereas decentralized architectures offer granular controls with increased complexity. Optimizing these aspects ensures seamless, efficient workflows.